Okay, so right now I'm going to take a look at the final exam for spring 2019, and this is question 6. This is a work-related problem. Okay, so let's read through the question and then decompose what they're asking about. So tank having a shape of an inverted right circular cone, so it's like this. We're told that its vertex is at the bottom and its base at the top, and it's buried underground. Its height is 20 feet. So here's 20 feet. And its radius, which is always its widest spot, is 5 feet. Okay, and it's 10 feet below ground level. So this is ground level, so this is 10 feet right here. Okay, so what we want to do is it's built only to a depth of 8 feet, and it has a liquid with a density 64 pounds per cubic foot. Okay, so because it's in pounds, right, pounds includes gravity, so I don't have to actually multiply gravity again because it's already there in my units. It tells me I don't need to worry about it because it's already there. All right, so we want to be able to find out what's the work required to pump this liquid to the ground level. So we're going 20 plus 10 feet. We're going to make the assumption that it's going to follow the same geometry as we go up. So I've got, it's a circular cone, which means that the area is going to equal to pi r squared. This is our cross-sectional area. But our radius is going to be changing, right? So the radius here is much smaller than the radius here at the tippy top. So I need to have a way of relating the radius. So I'm going to draw a similar triangle. So at its biggest, my radius is equal to 5. My height is equal to 20. Now, depending on where I'm at, maybe my radius looks like this. So this is my radius, and this is my height, right? Because I'm lifting the water up and calculating these cross-sectional areas as I go this way. So I've gone up a certain height, and then my radius is a certain height right there. So I can set up a proportion directly for how I'm going to relate these two triangles together. So I'm going to say my radius, when my radius is equal to 5, my height is equal to 20, and I'm going to solve for this radius right here. Over 4. Okay, or we can call it, y if you want to. R. I think in our solution set, maybe we call it y, I don't remember. Okay, so now it's h over 4. So now that's the radius that I'm going to be plugging into pi r squared. So the distance that we need to travel is going to equal to 20 plus 10, right? So I've got 30 total feet that I need to go. But like we said, the liquid that's being transported from here doesn't go the same distance as the liquid that's being transported from here, okay? So I need to take into account where I'm actually at in terms of my height. So the total distance that I'm going to go is going to be my total distance that I need to travel minus where I'm actually at, okay? Because this is basically the height of that cross-sectional area that we're going to be integrating as we go. All right, so let's set up our integral. So the volume of water is going to be 0 to 8. That's right, we're filled up to the 8 feet essentially. I've got pi r squared. I've got the density times the distance. And then I need to do that little thickness, the dh of my, my thickness slice. So I'm going to plug things in. So I'm going to go 0 to 8, pi r squared. So this is h over 4 squared times our density, which was at 64. And then the distance is 30 minus height times dh. And I think you can use dy, you can use dz, whatever variable you want to actually use for that. Just keep all of your terms consistent. And we're asked just to come up with the integral for it and not actually evaluate it. So I'm going to leave it at that.